Pleasure to be here. Let me thank you, Ali and Stefan and Kevin. Fantastic hospitality and an environment here. I've already benefited by not only learning more bids, but also algorithms from Stefan. So I hope we can work more together and productively. This idea of fire detection from space, it's not a new idea per se, but what we did, I think our group did, was show, in fact, how strong the signals are, how easy it can be, and how it should be done. I would posit that all good planets in the galaxy have fire detecting satellites, and we should catch up with them. Anyway, so here's the idea is that we have a system called FUEGO. It's an acronym for Fire Urgency Estimator on Geosynchronous Orbit. It can sit out there 24/7, you know, particularly during, it can't see through clouds, but it looks in the mid-infrared range, around 3.9 microns. There's a nice atmospheric window there. It can sit, and it turns out that the signals are so strong, you know, that you get a million photons per second with a mirror this big out there at 25,000 miles. I mean, it's just huge signals. And I think the kind of skills or enthusiasms or maybe naivete I bring from astrophysics is we sit and we wait hours to get 1,000 light particles from a supernova a billion light years away. We're so, oh wow, we got 1,000 light particles. So when we started looking at the signal noise levels here, we're impressed with how strong fires are, how we might be able to slowly work our way up the system. Probably as many of you know, satellites are, you know, kind of heavy metal of the space industry and take decades to plan. But in fact, there's been some breakthroughs in satellite deployment that are very encouraging, where smaller, cheaper satellites can be put onto buses. The Air Force has done this quite successfully, and we might even be using some of their data. So I'm hoping, you know, within a decade we can see progress towards a space-based system. Just a little, so FUEGO, we're the system. Graham Fleming kindly supported us with, he helped fund Marek Jakubowski, who was a fantastic graduate student, and Maggie Kelly, one of our collaborators in the College of Natural Resources. And again, what we're looking at is to try to see if we can see fires earlier. The answer is that we think we can reject false alarms enough. Again, that's the big question, because you have a lot of light. False alarms enough that we could see about a 10 square meter fire, you know, 10 feet by 10 feet roughly, area of a sandbox size from outer space in every few minutes. I mean, Ali raises the question, well, you know, will it help? I mean, can you put it out enough? And there's kind of a magic window to our mind. You know, if a fire's growing at a few hundred feet per second under Santa Ana, if you can get to it within half an hour, you can cover it maybe, you know, you could, with aerial tankers and ground crews, it's not turned into a megafire. And megafires are really the evil part of the whole business here. They do most of the damage, most of the cost, most of the pain and suffering is caused by these big fires. Hopefully we can get to the point where we can help, you know, with also computational predictive tools, we can understand when a fire might be dangerous or not. And you know, CAL FIRE is a large, very effective organization. We're trying to meet with them and talk with them and start to play a little bit bigger role in their day-to-day running of things. We're not just this 10, 20-year away satellite, but we think we can be useful now in a big data way. I mean, one might argue, in fact, that's where the real low-hanging fruit in fires over the next decade will be, is in data management. So, again, well, let's see. So here's actually just a little back history. I co-advised Saul Perlmutter with Richard Muller. He was started as a graduate student in our group when I was one of the leaders of the Supernova search. So we started out Supernova, and it's relevant, I mean, not only for Saul, but also the fact that finding point sources against a cluttered background is something, you know, we've kind of done most of our life, although with much more primitive tools than Stefan has now. But we'd be looking at many images of a galaxy, look for a few pixels that are bright, that seem to have some nice characteristics, and then if it looked like a supernova, we'd turn other resources on it. That kind of sounds like what happens with a fire from outer space. You look for its reality, do test, you know, look at hyperspectral imaging and time development and other characteristics, and eventually you could understand if this is going to be bad or a false alarm or it's going to be something real. We even have a patent filed on some of our algorithms, which apparently I'm told, actually you'll run this in the talk, the Department of Defense has very powerful satellite resources up, and somebody says, oh, I mentioned our patent that we filed for, University of California filed for it, and they said, oh, DOD knows all about that. I said, anyway, so that's just some, again, here's what we've done in the supernova world. We had our first audit, we also, it turns out, we had to automate telescopes, automate image processing and scanning and all this stuff. And we had the first successful automated supernova search back in '86, and it was in this galaxy here. So this was the first supernova totally found by automated means, again, which will be like fires. Okay, and we moved it to a deep supernova search in Australia. Saul was part of this work, the Anglo-Australian telescope. There's just some history. Again, a subtext of this talk is that there's been tremendous development in image acquisition. You know, well, often because of Department of Defense initiatives, but the commercial sector has caught up, industrial section, and you know, huge arrays of things, microbolometer arrays now that would have been a fraction of $1 million now are a fraction of $1,000, for example. So there's just been factors of 10,000 price reductions in detectors at all wavelengths. So this is really exciting. Again, they're all coupled to computers and image processing and stuff. So I think that the sensor question has been tremendous progress on, and that's going to help us. In fact, I mean, again, there's sort of a subtext. We came into the supernova business. We said, oh, we have microcomputers, PDP-8s. Stefan doesn't know about those. we were the hot kids on the block because, yeah, we were using a microvax, and you know, we could afford a microvax and a 400 by 400 CCD. We were the envy of many astronomers doing this. And actually, there's a similar tale here. We were kind of outsiders, you know, physicists and stuff, trying to go into astronomy. We met with a lot of, well-justified skepticism about our ability to do the field. So I think, so here we are kind of outside, you know, we're data people kind of coming into fire business, but we're treading a lot more softly. I have enough scar tissue from the supernova experience that, you know, we're working with people in the field, and we will be meeting CAL FIRE people in Sacramento this month, I think. So I think we can learn from that. Here's again, this is the instrument being mounted on the Anglo-Australian telescope. And eventually it moved to the Canary Islands. We had bad weather in Australia. This is a 2.5 meter Isaac Newton telescope there. That's where we found our first supernova. That's actually, and then Saul took over the experiment at that time. He was a more skilled manager than I think, and a better communicator. So that was good. So here's the Nobel Prize. He kindly took. He was great. He took all the kind of founding members to Stockholm, or the whole team to Stockholm. So I've never seen so much alcohol consumed in my life. But anyway, then back to FUEGO. So actually working with Merrick and Maggie and Scott, you know, the real experts on fires, we probed a number of data sources and found, you know, even though there were backgrounds from these satellites, we have weather satellites. The GOES satellite is taking images at a pretty good clip and providing us, it's a test bed, and also MODIS satellite. That was a low Earth orbit, but it was imaging fires pretty much. And we put all this data together and showed that with some algorithms on time development and spatial characteristic, we could repress the backgrounds enough that looked like we'd have a credible case for fire detection from space. And again, all things have gotten so much better since we wrote this paper. So that got refereed and published. Oh, and again, where we are in the sensitivity and the world in the United States does have a lot of powerful satellites out there, but the FUEGO satellite, we'd want to sit down here, be able to revisit a target every minute or so, and also go down to about a megawatt fire, much more sensitively. Even GOES which will be one of our nation's most powerful satellites, we should be able to operate, mainly because we've optimized the satellite for fire detection. We should be able to go down 10 or 100 times more sensitive on that. Now, and we're working with GOES our scientists, data scientists. Chris Schmidt is at the University of Wisconsin in Madison. He's a collaborator on this. Has really helped steer us and direct our efforts to a large degree. The fire community, actually Elaine Prinz was one of the leaders in this movement. She was at Madison, and they always had to fight against the weather people. We got a hurricane coming, and they would tend, the whole data flow, the whole workflows through the satellite, getting data out quickly and intermittently is just a tremendous nightmare because it's optimized for hurricane prediction, I think. Or, well, I'm probably speaking a little bit beyond my knowledge, but it's been, Chris has struggled valiantly and successfully often to be able to get the data out of these satellites. And in fact, that's getting better and better. Future satellites will have more and more capabilities, and Japanese satellites coming up. So I think actually the existing satellites, in fact, will get better and better and have these kind of capabilities. So here's a example of a fire tanker, aerial tanker in action. Actually, although not with this airplane, but there's also been recent progress in getting refurbished DC-10 super, big airliners converted into aerial tankers. There's a company down in Albuquerque that's doing this, and that means you could get to a fire 2 or 3 times faster, dump a heavier payload, and have a bigger impact. So they're kind of a natural synergy with our fire detection system. We could, if we see something quickly, we'd want a quick response. So here's just again, it's really a global problem. This is from Chris. This is from a talk Chris Schmidt gave. Some fires all around the world here. Various regions. The usual deforestation fires in Brazil. He says actually he went and gave talks about all the fires being burned in Brazil, and actually he's scared. He can't go back there and talk about this anymore because he's built up enough enemies in Brazil that he's not respected there or not appreciated there. Let me just look at one example of where systems like ours might have been somewhat useful. This rim fire is an interesting example. Actually, here's a picture of it on the GOES satellite, which again, it saw it pretty early. It could have seen it pretty early, although we didn't get the data out until like a month later, and the workflows were not made for this. But GOES could see the rim fire. This turned into a megafire, 3rd biggest. And I think megafires are something more than about 50, 100,000 acres of fire. And they do most of the damage. But it was very interesting. The started, I guess, by a campfire, and it was reported by an aerial tanker, Cal Fire tanker, flying to another fire. He said, "Hey guys, you can call radio, and there's a fire over here." And he flew onto his fire, and but again, you could imagine if you were coupled into a simulation system, people could look at the moisture and the winds and everything. Somebody might have said, "Hey, put your water down on that other fire," but it didn't. It got out of control, did a huge amount of damage. The suppression costs were $100 million, and then question.
In other words, it was reported later than
yeah,
FUEGO could have reported.
yeah,
So FUEGO could have reported at 325, got reported at 650.
yeah, yeah. I think, we could have seen it a little bit earlier than those guys. Hopefully again, well, we had to have that. I don't want to oversell our capabilities. I mean, I think we're probably an evolutionary step, not revolutionary, but you still have, probably would have taken, minimum half an hour, 45 minutes to get an aerial tanker right there, except for the one that was flying right nearby. So again, the suppression costs were $100 million. And then this doesn't seem to be well known, and it became very apparent. It turns out that if you look at the real amount of dollars spent on fires, it's typically between 2 and 50 times the suppression cost, and somehow we all pay for that in societal cost, insurance, it goes into state budgets, and we don't know. But I'll still have another slide about where all that money disappears. Housing. I think this WildFire did $1 billion worth of housing fire. Again, we're paying for that in our insurance cost. So again, Scott Stevens is a world expert on fires and gives this is in fact is from his one of his talks. But in the 40s, we decided we adopted what's called the Smokey the Bear policy, that we'd start to put out fires. And that's a arguably good thing to do, but also it kind of tilts against what the natural role of fires are in ecological systems. And that is that, Scott has very interesting stories about how Native Americans, indigenous peoples in California would set fires, and at a lot higher rate than we see now. But if we put out fires, the grass, underbrush, forest fire, forest pine needles stuff, all this stuff will accumulate, and when fires burn, they burn with a much more ferocious thing. I mean, this valley fire, people were amazed how fast it spread. I mean, even with a moderate wind, it was going much faster than they thought, because we've been in a drought for so long, and fires had been suppressed in that area. For example, some of the fires within the national park system will let fires burn, is well known. Apologize to experts in the field, but national parks will let fires burn, and when their fires go off, they're much easier to, at least to contain or boundary. They do a lot less damage than a fire right outside the national park boundary. And Scott has lots of data on this from Yosemite. And again, but and actually, the Cal Fire does an amazing job. I mean, they're almost an A+ student. They're putting out 95 to 98% of the fires very effectively. But it's those few percent that escape that are kind of problematic, which also links to the whole predictive, what our needs for a data-driven fire response system cries out for. Fires are not particularly, we don't have a lot of evidence that there's more acreage being burned, and this is way too noisy data to make any statement about increased fires. But for sure, the fire suppression costs are increasing, both because of normal inflation. Also, in California, we tend to put a lot of effort into protecting, the urban wildland interface. And those are houses, and when fires eke into those, there's a lot more money put into putting these fires out. So we're spending several $1 billion a year on suppression. About half of that's in California. Actually, and California does not have the most wildfires, but it has the most expensive. Half of the suppression costs are in California. Let's see. And then I think some of you have seen this already. This is a graph from a publication that Scott was on with other collaborators, but they looked at what fractional increase. I apologize for the quality of this graph. What fractional increase in fires over the next few decades would result? And it's kind of interesting. You'd see areas as the climate warms. This is within. They have several predictions based on several climate change models, but this is one typical one. But places like Humboldt will be somewhat closer to San Diego, LA area. In fact, I mean, maybe interestingly enough, San Diego, LA can't get any worse. They're already maxed out in terms of climate change isn't going to make any difference. They're toast already, but more ways than one. But places like Humboldt, Northern California, we're going to see a lot more big fires if we keep ramping up on the climate change. So that's of concern, I think, for all of us. Oh, I had a little. Let me see if this will play. I don't need any. Where's my? Here we go. Is that coming across? This is from. Whoops. Did I have to detect the detector again? Can somebody?
Grab it and move it off the screen.
Move it off the screen?
To the right or the left, it might be the extended test.
Okay.
Keep going.
I apologize. I should have tested this. Did we get it? Now, if I go full screen, will it disappear? Okay, so well, you can get the idea. This is just a little sense. Stefan has friends in South Africa. We're really a global problem. It looks like, let's see. So let me play it again. This is it's easily found on the NASA website. Did it disappear?
No, look at it. You have to watch the screen.
Okay. But this just shows the seasonal variation of climates over a year. As summer in the north comes, we get more up there. California wasn't so bad. I guess this is 2003 when this was. I guess we didn't have that bad a year of fires. You see Africa, South Africa, a lot in Brazil in summer. I guess that Philippines, Indonesia, but it's a cute. It's kind of a scary, cute thing. Let's see now if I go back to. Oh, look at that.
Why do you get such a big effect over the equator? In Africa, for example. There's a big gap between the equator. Well, there's the jungle.
Yeah, I wonder if you run into the jungles like immediately sub-Sahara, you have more, scrub or more stuff. And then in the jungles, they're too wet to burn. And then you jump down to the Serengeti. But Indonesia has a huge number of fires. Philippines, many human set on purpose and stuff. But it is a global concern. Let's see. So, now how do I see my cursor again? Oh, there. Okay, good. Okay. I apologize. It's such a well-run group, and I'm klutzing away here. Okay, so anyway. Oh, this is an interesting one. It wasn't, probably just on the boundary of Megafire, but again, it was, this is an example of a fire over a really, droughty or dried out region. When it ran, it killed 95% of the trees. And you end up with this, and as Scott says, well, this is going to take a century for these places to come back. So that's, again, kind of scary. So, again, I've talked about the financial impacts that are growing. Acreage burn, not so much. Let's see, and again, it's all in a few of these megafires where things seem to happen. Again, we've talked. Also, you'll get places when you have multiple events, multiple fires going on. Where do you put resources? Where's the action? And it's sort of become apparent that there's a benefit for society if we can have very good, high-quality infrared data of a fire that's ongoing. We know every pixel is telling us how much energy is in the fire. And then I'll come to next to the data layers that go into the simulation programs. But if we, for example, if we really knew what was happening in a fire, and we had good pre-existing GIS data all prepared, then I think it would make this whole issue better. This is a little too detailed, but again, we hope that we can, with the detection and also the ongoing monitoring of fires and running simulations, at some point, this will take, I'm sure, a number of years to get us into a reality that we can be assistants to the incident commanders. The incident commanders I've been told by one of my collaborators, you have to come to a fire. And these guys are balancing all sorts of stuff, where to put engine crews and, where to put airplanes, and, they have a very, very, very hard job. And then to have them sit down and, our kind of life, look at a workstation, look at surface plots, run a few simulations, have a cup of coffee, talk to somebody. Does this make sense? Kind of, the kind of blessed academic life we live here is not in the life of an incident commander. So you can imagine there are cultural, we have to be we want to be very respectful of what the current systems are, which largely work, and see if we can slowly migrate in and do something effective. So, again, here's this one example of the San Diego fire I mentioned. See the fire suppression there. This is remarkably tiny cost, 2%. And the real cost to the rest of the community was huge. Unemployment insurance is 17%. About 50% was loss of property. So there's a huge multiplier on how much damage is done to civilization, and we all pay for that. Society pays for that, even though it's not clear how, but it comes out of a lot of stuff that we depend on. Again, I mentioned some characteristics of FUEGO. One thing that comes up here is that we've had, I think, a productive dialogue with some of the people in our United States Air Force who have a satellite system called CHIRP that actually not flying now, but there might be something like it up there now, and I don't have any security clearances, but these satellites, in fact, do provide close to the kind of sensitivities we would need that are up there already. And we're hoping there's some way we can work with them, that we can use some of our algorithms, some of Stefan's algorithms, on the existing satellites, might be processing on their computers behind the wall, but we can get out alerts from them. In fact, there is a system, a very good gentleman named Everett Hinckley from the U.S. Forest Service has in fact worked with a number of the military and classified satellites in space, and they're sending out alerts effectively. Again, a lot of his job was to suppress the backgrounds, again, which I think, I hope the machine learning tools we've talked about can have real significance there. Let's see. Oh, and again, drones, we got in the newspaper over drones. Turns out that, drones you've come to learn, are amazing data tools. You can sweep up huge amounts of data. And, there are significant FAA worries and firefighters' worries. There was one fire, a drone came in, and almost, the guy, it freaked out a bulldozer operator, and he almost tipped the bulldozer operator, over. There have been near misses on drones coming in, and Cal Fire's helicopters have had near misses in airplanes. And so, again, the whole atmosphere of a fire is so much, there's life-threatening and property damage and all this stuff going on. Then having an amateur come in, fly a drone to look around is really, is not a good solution. So I think that's given drones in some ways it justifiably, create a lot of skepticism about their use. But in fact, there are ways they can be used immediately. For example, the mop-up operation after a fire. You can fly a drone with one of our infrared detectors. We're working with the teams that have these drones and infrared detectors, and they can see mop-ups that are costly and they're not dangerous, but you have to go and find all the hot spots. That's actually such low-hanging fruit for a drone and a detector data system. You can see 1-inch embers easily from the drone at 1,000 feet. These systems are so sensitive. Again, and I mentioned, in as much as FUEGO we'll be, 5 years, 10 years before we can even consider building our own satellite. We're looking at all these things in between, and again, we're working with a drone company and a good company that integrates data systems with the drones in Reno. And actually, this team has made significant progress on infinite duration drones that, Google and Facebook and a lot of IT companies are planning, long-term either balloons or drones, which we've talked about. But this company has something light and cheap and ready to fly now. And I think it's conceivable that within a year and a half, they can have a drone that could fly at 80,000 feet forever. Solar, and there's some algorithms, there's solar and recharging, and they have some other patented technology that could keep these things up there. And one like that could sit and look at all of LA County, for example. You could have one drone every one over San Diego County, one over LA County, et cetera, with probably 1 foot pixels. And that's all very, very possible now. So I think that's something we can do very quickly. Data will play a huge role in it, and maybe I hope we can form some working collaboration with BIDS on this. I mentioned the history. We got into this from the supernova side and the Oakland fire, but at the time, the infrared detectors in '89 would have been $1 billion just for the camera, and probably another factor of 2 or 3 on top of that for the satellite. But things have gotten a lot cheaper. Both existing satellites out there seem to be willing to share their data. Well, this T4SAC, it's an interagency coordinating committee. Turns out that there are half a dozen agencies, at least, federal and state, all involved about fires, and they never talk to each other. So this is a group actually we've become part of, and it's helped us get a lot more understanding of how we might be possibly useful in this business. But anyway, so again, we learned of some of these drone collaborators who we're working with right now, and that's been fabulous. Also, and through T4SAC, we learned of the San Diego wildfire towers and a good system called HP-REN, where they have cameras on fire towers that are can cover a huge amount of San Diego looking for smoke. And it turns out they're mainly used now for confirming fires. If somebody says there's a fire, they'll get a call in, then they'll look at, try to triangulate with two towers and confirm that there's a fire there. And we're saying, wait, how come you're not looking for fires with these? That's what you do. And it's, well, we don't do that. So actually, they didn't have enough resources to develop a automated fire detection algorithm, and I have students working with now, and again, hopefully we can make some progress with Stefan on this. So, and here's some of the team. We have people versed in GIS. This Bill Cruz is a really good GISer. As I mentioned, this company Fireball is in Reno, and Drone America is there. Work with University of California, San Diego Supercomputer Center. That's Ilke Altentis, and mentioned Drone America. A woman who used to work at VMware and is a cloud computer specialist. She has, they call them workflows. She has our workflows working on their system already with data aggregation and data simulation starting to work. Again, so I think our long-term goals are to eventually get there, but we don't have enough credibility to justify a satellite yet. But I think over the next 5 to 10 years, we'll develop that baseline of information that we could develop a satellite. And again, we want to take advantage of a pretty large amount of data that exists out there. These military satellites, we will soon have some access to that, and also working with the drones and the infrared dating systems. It turns out the Forest Service has a pretty good system called NIROPS, which once a night will fly out over all the fires. There are a number of fires in the western United States. It'll go and survey them all. It's based out of I think Boise, Idaho, and but that's not enough information. I think what comes out is a perimeter. Really what you want to know is how bright every pixel is at high resolution. And so we're trying to hopefully support and build on the good work of NIROPS and the Forest Service, and again, the drones. And we have a system, Tim Ball, a Fireball, a collaborator, has airplanes now with very high resolution imagers, and hopefully that can supplement NIROPS and make our simulations a lot more effective. This, again, we have a lot of activities, again, trying to probe various places where our use of data and algorithms could be helpful. Oh, here's, again, this is an example of a workflow diagram. I think this is public knowledge, but there was one of our collaborators was in a fire situation, and their GIS data, their input data, was going into the fire simulation program, and it looked like it was going to be a pretty fast burn across this. So I think they alerted some folks, but then it found out this one area, turned out they thought it was a grassy field, turned out it was a reservoir. So there'd be very, very little chance of any fire damage or anything like that. But they had taken that input data from a federally maintained GIS site. Again, it just shows the kind of issues in data validation, qualification of this, and that's why there's really work at almost every piece. I also work in science education in high schools and middle schools, and almost every stone you overturn in the system has lots of really wiggly things on it. And I think there's, like many things in society, same can be said that there's a lot of room for improvement in how we handle data with fires. And again, I mentioned we're going to use the existing fire products, try to really get the best GIS data. Again, there's pretty static stuff like contours won't change, but winds will be changing. Even fires will generate their own winds. We have some algorithms we want to test on fire-generated winds. And we kind of make this thing detector independent enough, particular computer-based system independent so it could run in the cloud and be of use wherever. So that's, and here are some of our, this is from Bill Cruz, one of our main data guys. This is what we want to do within the data management. We want to be cloud deployable. We want everybody, like a firefighter, to be able to look down and see, the fire's coming this way. I mean, not only the incident commander, but most of the firefighters have smartphones. And an airplane flying above can be a local hotspot for communication. There is software out there for doing that. So we can, these problems like in Colorado a year or two ago, fire came down the canyon and wiped out a whole bunch of firefighters, and a real tragedy. But that's something probably, again, with modern detectors, modern communications, that could have been averted. Let's see, again, the system UCSD, that's another talk in itself, has a really wonderful system called WIFIRE, which again aggregates data, handles the workflows, collects data from the towers, and pushes data out to the incident commanders and the firefighters and the community for evacuation plans. So I think that's we're building, we're kind of riding on their coattails and trying to support WIFIRE to the best degree possible. But that's a superb system that I think is going to get better and better. And they kind of view us that we bring some of the algorithms and the sensors, like I mentioned, that where our hopes to be able to find smoke from their watchtower system might be a somewhat added asset to the system. So here's again, Bill made this picture of the data flows, including the real-time sensor input, the data services, the GIS stuff, which is up to date. Then we'll have cloud services that should be independent of a lot of this stuff. And then we want to be able to get eventually, we're not there, and I think we're, at least a couple of years away. To be able to send something out to the incident commander after we know that things are working, our simulations work, saying, well, put assets here. They want something very simple and quick. They don't have time to look over these things. And I think hopefully our software stacks will be mature enough to help undertake this. And this is more than you need to know. But again, Bill, we've gone into some of all the possible inputs. I thought this was cute. The LiDAR products. So the Bill Cruz, our collaborator, and he's in a small company on the peninsula. But I think working with the Save the Redwoods, he's mapped every redwood tree, I think, in Marin County. The cloud is very big and spacious and can give us exquisite knowledge. So, imagine, if you know where every tree is I think it's a lot of work to dig that, pull the points out of the cloud to do that. It takes it takes a lot of cycles to generate a tree. But I think, with GPUs and advanced systems, if we know where every tree is, where the wind is, how hot it is, how likely it is, we're going to see huge, I think, substantial advances in the simulations. There's a number of fire simulation programs. One of the best tested and probably pretty reliable is a program called Farsight. Comes by Mark Finney from, from U.S. Forest Service. But here's some of the parameters that go into this, the data layers that go into the simulation programs. Things you might expect, the elevation, slope, the fuel model, the crown, all these things about trees and forests that you need to know that will predict what's going to happen, including the moisture. There are things, moisture and the local wind and et cetera, that are also inputs into this. But it's probably done everything right. It's used a fair bit, but the validation is still not very good because he doesn't get good enough data input. And we say we want to get resolution of meters, at least from our airborne UAV systems, meters to send in them. He says, oh, that'd be such a blessing. But right at the present state, I think that computationally we're ahead of the sensor and the data input with Farsight. I think it's probably a very good program, but it needs, right now in some ways it's garbage in, garbage out sort of situation. I think that's going to improve a lot over the next few years. Again, there's been, this is some of the algorithms on that Chris Schmidt has deployed for GOES, for example. We're working with him. So, again, I think, I view about the end of the period here, yeah. So we want to get this GIS, probably particularly for San Diego, get the GIS data together for them, vet it, make sure it's in great shape. And the next fire, when we have a little bit of funding, we want to fly and get exquisite. We can get 100. It's kind of sad, with a few thousand. Well, it's about $5,000 a day to rent the airplane and the cameras. For for doing one fire, we can have 10 or 100 times the best data ever collected on a fire, which tells me how vulnerable this field is for improvement. So then we'll be doing this data experiment. We don't want to bother incident commanders. We'll map the fire, run it through our simulation programs, as the fire goes on. See how good our predictions are. See if our predictions for the fire actually match what happened. That would be a first. So that's kind of, I hope it's sort of a conservative goal of where we're going to go. So anyway, I think, again, that's it's an area that's been kind of unplumbed. When you see how the silos of government funding has gone, and we go to government agencies and they say, oh, it's a great idea, but we're on continuing resolution or sequester. We say, can we have $1,000 for this widget? And we get laughed at. So, but I think we're still trying. We have 2 NASA grants in right now, and it might be an SBIR we'll be applying for in a few more months. And we've been in conversation with some venture capitalists who maybe on the drone side see this as low-hanging fruit. By the way, one of our drone collaborators has just made some progress with a power line inspection. In fact, there's cash flowing in that regime already. So I think that tells us that besides the wine industry, there are viable uses of the data management with drones. So again, I'm delighted to be here. I've just appreciated the quality of people and the interest here, and I hope that we can find a way to work together and advance society. Thank you.